my Van de Graaff generator. See? The 0 volts, it's impossible. Something's broken here, huh?
Nothing is broken. What is that thing?
Hi.
Okay,
How
hi.
do you measure?
Today I'm reacting to Retro Boom videos. Yay. Yeah. Okay, so...
High voltage. Of course, you can use a multimeter to measure like 120 volts. If you can even call this high
That's
voltage.
pretty high voltage.
Of course, we can probe the voltage. I have blown so many fuses, leaving the meter's probes in current meter trying to read voltage. Check your setup before committing to something. On the other hand, it is the best time to commit to my sponsor Brilliant and learn from all the math, computing and science lessons they have available because, well, your brain is not getting any younger, so use my link to sign up and start learning for free. Anyway, these devices are designed to be able to handle 600 volts or 1000 volts, which is pretty good, but I'm talking about tens of thousands of volts, not just the pure 1000 volts. Of course, the simplest way is to divide the voltage down below what your measurement device can handle. A resistor divider is the way to go, where the input voltage can divide between two resistors. Here, I'm lowering the 120 volt AC down to 1.2 volt AC. And if we can measure the... Oh, damn it. Oh no.
First try always blows for the Retro Boom.
You must pick resistor values that for a given voltage only consume power below their power rating or they'll burn. These 100K, 1K resistors should be good though. There you go. Yeah, with these values, they remain cool.
Don't touch live circuits.
It is always advised not to touch live high voltage. So we have around 1.14 volts across the small resistor, safe enough to feed into a microcontroller for measurement. Same divider trick can be used to measure very high voltages like on my Van de Graaff generator. See? The voltage will go over the resistor divider and...
Do you have a ground on that thing?
0 volts? It's impossible. Something's broken here, huh?
What's that thing? What the heck? Oh,
the issue is the voltage builds up high on the Van de Graaff as the charge is being pumped on it at a slow rate. These resistors, though, although they are in hundreds of kilo ohm range, suck charges much faster than it can replenish them. So the voltage drops to almost 0. This is an important point. Every time we are measuring anything in the universe, we are taking a sample of it to look at. And that action changes the levels we are trying to measure and causes inaccuracy. We have to keep that in mind and minimize the measurement impact. Perhaps I can use my man-made driver, which can maintain a much more powerful output at around thousands of volts, so my measurement won't affect the output level much. So I'm using a 10 mega ohm and a 10 kilo ohm resistor to divide the voltage by almost 1000 while limiting the power draw from the output. And I keep the outputs apart to prevent arcing. We turn it on and...
Yep, it arcs. More funny faces!
High voltage can arc across short gaps. It was easier for the electrons to go over the air than through the resistor.
Okay, get new resistors.
Which means we have to use resistors that can handle high voltage. Look what I bought.
Oh.
I got 20
resistors,
each 100 mega ohms. I've never held so many mega ohms in my hand. Except maybe for an open circuit. Each one of these resistors can handle 7,500 volts, and I'm gonna put all the 20 in series to get 2 gigaohms.
The gap is still small between the two leads of the resistor, so I think it's still gonna arc.
That should be able to handle 150,000 volts. Let's start soldering.
Don't burn yourself.
There we go. Such a huge resistor.
Okay, now put it in oil insulating oil. That would be amazing if you could just put in insulating oil, put a PVC tube over it, and call it a day. My neck hurts.
Problem is that if I in fact place 150,000 volts across this, the voltage between each resistor is still so high there will be corona discharge everywhere and affects the voltage reading. But I have a plan to insulate it better. I bought a bunch of rigid reusable plastic straws that stay quite straight, and I have a syringe that looks like it's made for these straws because I can pretty much...
Are you trying to suck air out of it? Because when you remove air, it makes it more conductive. Like, it will arc easier without air, I think.
Screw them on top of this, like this. It is quite convenient when things come together quite randomly. I pass my resistors through the straw, mix enough of my 2-part epoxy.
Oh! I thought you were going to suck the air out.
Pour it into my syringe.
Well, there goes a perfectly good syringe.
I stick my straw on it, screw it tight, inject the epoxy.
That's actually smart.
Straw, and hopefully there won't be any bubbles in there.
Why didn't you use a vacuum chamber if you have one too?
Extra. No worries, now we'll put it to the side and let it dry. Okay. Today is tomorrow and everything is dried up. And I wasted so much epoxy. I guess I forgot that the resistors actually have volumes too. Now we cut our resistor from the syringe. I guess I can put this ball thing at the end of this thing as well so the resistor pin doesn't break. Like this. So I have a 2 giga-ohm resistor here that I connected to a 2 mega-ohm resistor for an almost 1000 to 1 division ratio. Let's test it. First off, I'm gonna test it at a much lower voltage of 120 volt AC. So right now, my input voltage is around 114 volts. And if I try to measure the output of the resistor divider...
Use a 1 ohm resistor connected to that.
Eh? What is this? This is like 400 millivolts already. So I'm expecting my 120 volt AC to divide to 120 millivolts, but I already have like 400 millivolts on the resistor output, and if I connect this, it actually drops. What the hell? Not only my noise levels are so damn high because of the huge resistors I'm using, but also the input resistance of this meter is probably loading the output down. Let's reduce the 2 mega ohm resistor to 200 kilo ohms so that the noise level goes down, but at the same time my division ratio goes to 10,000 to 1. So my signal will be 10 times smaller. But at least with the 10 times smaller resistor, hopefully the input resistance of this thing won't affect it as much either. So right now, without the AC connected, my noise floor is around 37-38 millivolts, much higher than the 12 millivolts I should be seeing if I connect the AC. It seems like my big resistor is just acting like an antenna, see? I bring the wire close, the voltage goes up, and vice versa. The hell? Let's just go to high voltage measurement. Measuring my circuit that can output almost 10,000 volts, I should be able to see at least 1 volt at the output of the resistor divider, which is much higher than the noise floor. And of course, it outputs AC, that's why I'm using a scope. So my outputs AC, that's why I'm using a scope.
What happened?
So my 200 megahertz scope probe has 15 picofarad minimum input capacitance and also a 10 mega ohm input resistance, which is fine. It is much higher than my 200 kilo ohm resistor, but the capacitance... Let me explain. For this circuit, the RC starts filtering at the cutoff frequency.
I complained with my grandma.
Voltage drops by 3 decibels. Ignoring the much larger scope input resistance, the cutoff frequency is 1 over 2 pi C R1 parallel to R2. And with R2 being much smaller than R1, we can pretty much ignore R1. So with my 200 MHz probe that has a minimum of 15 picofarad input capacitance and my divider's 200 kilo ohm resistance, I'm filtering anything above 53 kilohertz. Which is not bad since my driver's output is around 30 kilohertz. Of course, there is another way to make the divider frequency independent by adding parallel capacitors, which would also filter more noise. I don't like it much though, because capacitor impedance drops by frequency loading the high voltage. So for now, I'll stick to my method. Okay, you know what? Screw all the noise and messiness and complications with AC. I just added this series of high voltage diodes and a capacitor to rectify the AC output of this device, and we will just measure in DC.
Probably.
So we just turn it on.
Just like I thought.
Okay, so the output voltage is already above the 15,000 volts rating of this capacitor. Let's reduce the supply voltage. How about now? How about now? Okay. What? 0.935. So we are measuring above 9,000 volts. Okay, let's move to my bandograph. Of course, this is DC, so no filtering required. I googled to see what is an accurate way to measure super high voltages, and they mentioned arcing distance between metal spheres. Because voltage around a sphere is pretty uniform, and we know in that case the air breaks down and arcs at around 30,000 volts per centimeter of the gap. So right now I'm holding a distance of around 3 centimeters between the balls, which means the voltage between them can only rise up to 90,000 volts. But how far can I go if I allow the voltage to build up on the balls? Let's see. Whoa. How far was that?
Maybe a million?
Let's roughly measure.
Turn it off before measuring it, and also short it to ground.
Around 6.5 centimeters, so like 200,000 volts. Of course, 30 kilovolts per centimeter is not super accurate either, unless you can maintain the air pressure and humidity and temperature and stuff. But let's see if my resistor divider will do any better. First off, will this massive resistor load and drop the bandograph voltage? So now if I touch the bandograph, it stops discharging, and I'm reading only around minus 0.4 volts. It's like minus 4,000 volts. So it's not going to even discharge in like 2 millimeters. Very small arcs. Damn it! Even my 2 giga-ohm resistor is enough to discharge that voltage to close to zero, well, 4,000 volts. From that observation, perhaps the 200 volt estimate from the big ball gap test was close. Perhaps the ball test is the way to go, since it allows the voltage to rise to its maximum before it discharges. But let's try something for a better visual representation. I'll hot glue one of my straws to the top of the dome. We cut a circle of foil like this, then we put it on the straw like this. We cut a big circle of aluminum foil like this. Now hopefully it will fly. Perhaps I need a very small piece of aluminum foil. Like this thing? Nope, I made something like this that looks like a parachute. Let's try this one. Damn it. No, it flies too well. Ouch. Let's not let it jump out. What did I make? This wasn't the intention, ouch. Well, the point was that to build something that based on its height, I could tell the voltage. But when I connect my resistor divider to it, the voltage drops too low that it drops to zero anyways. On the bright side, I made some strange bouncy thing. Just realized I can add to the length of my straw. Here we go, it won't jump out anymore, ow. And depending on the voltage of the dome, it can stay at different heights. Okay, it's grounded. Whoop. And if I touch it, it starts bouncing. Down. Look at this. The voltage rises to whatever, like 200,000 volts or something. And when it discharges, the voltage drops and this thing comes down. I guess that's one indication of the voltage level. And despite having 2 gigaohms, it easily sucks all the charges out of this thing. So I don't know if there is any real way to connect a meter to this dome to, measure the voltage. Although the voltage is super high, the amount of charges are so low, you can suck them away. There is probably just a single electron on the dome. But hey, this bouncy thing is kind of cute. So I guess the internet was right. The most reliable way to measure such weak source of high voltage is to have, say, like a grounded ball beside it, let them arc and measure the gap between them and calculate the voltage. We learned something today, but I'm pretty sure you can learn way more and consistently every day at my sponsor Brilliant. And free too! Sign up from my link brilliant.org/electro. Many of us look to find really good source material to learn from for ourselves or our kids. Brilliant has them all in math, science, programming, data analysis and AI, teaching them in the most effective way. That is, in traction with what you're trying to and in a much safer way to
interaction with a power
is proven to be 6 times more effective than just watching lecture videos. And Brilliant is filled with hands-on problem solving, lessons that teach you from ground up, designed and crafted by an award-winning team of teachers, researchers and professionals. And they designed it to feel like a game with encouragement and achievements. So imagine you spend time having fun while learning what actually matters to you that can greatly help you at work or school. Like for example, I see a lot of people get into electronics by first learning how to program electronics. And what's a better way to get into programming than building a daily habit of learning how to code effectively through the Brilliant app? You can likely learn a ton of it for free by visiting my link brilliant.org/electroboom from the description or scanning this QR code. But don't worry, if you still need more time to finish, my link gets you a lifetime 20% off annual premium subscription. So you can learn forever. And thank you for watching.
Those are some nice moving eyebrows. Okay, video. Okay, what other electro boom videos should I do next? Tell me in the comment section and I'll use the highest like comment. Okay, bye.